We first consider the area under the graph of 1 over x. The first question is the area between the graph of 1 over x and the x-axis over the interval 1, infinity, finite or infinite. And the second question, if this same region is revolved about the x-axis, is the volume finite or infinite? Surprisingly, the area of the region described here is infinite, but the volume of the solid obtained by revolving this region about the x-axis is finite. In this part, we define the integrals over the infinite intervals, as well as integrals of functions containing a discontinuity on the interval. Integrals of these types are called improper integrals. We examine several techniques for evaluating improper integrals, all of which involve taking limits. To get an intuitive interpretation of improper integrals, we attempt to analyze integral from 1 to infinity dx over x graphically. This is the graph of 1 over x. And this is 1. This is the point 1. And the area goes to infinity, as you see. We let t, let's say t is here, be a fixed number in the interval 1, infinity. Then, by taking the limit as t tends to infinity, so we have integral from 1 to t dx over x. We write the improper integral. We re-express left-hand side of this equality. An improper integrals of type 1 is an integral whose interval of integration is infinite. This means the limits of integration include plus infinity, minus infinity, or both. Remember that infinity is a process. Keep going and never stop. So infinity is not a number. Therefore, we cannot use infinity as an actual limit of integration as we did in fundamental theorem of calculus part 2. We make the limit of integration a number. In this case, this is t. And we take the limit as that goes to infinity or minus infinity, according to the question. If the answer of this limit is equal to a number, then the given improper integral is called convergent. If it's not a number, if it is infinity or minus infinity, in this case, this improper integral is called divergent. An improper integral might have two infinite limits. In this case, we can choose an arbitrary point C and break this integral there at the point C. As a result, we obtain two improper integrals. If for some real number C, both of these improper integrals are convergent, if both of them are convergent, in this case, we say that the given improper integral is also convergent. If one of them is divergent, in this case, the given improper integral will be divergent. Let me summarize this type. If the interval of integration is not bounded, in this case, we cannot use fundamental theorem of calculus part 2. This is why we have improper integrals and we have all these techniques. Let's try to understand the first type by some examples. This is the first example. And the rule is given here, as you see. We first write the limit version of improper integral. We say that Instead of this infinity, we use a variable. Let's say t. So t tends to infinity. We have dx over x, integral from 1 to t. Now we have the bounded interval for this integral. This is why I can use fundamental theorem of calculus. What is antiderivative of 1 over x? This is ln x. So limit when t tends to infinity, we have ln x. X is from 1 to t. This is equal to limit t tends to infinity, ln t minus ln 1, and this is equal to limit t tends to infinity. Since ln 1 is 0, we have ln t. Now please remember the graph of ln function. This is something like this, and when t tends to infinity, the graph of ln function keeps getting larger and larger. So the result of this limit is infinity. Since the result of this limit is not a number, this integral is called divergent integral. Divergent integral. Let's look at the second example. I give the rule here. Okay, again. Now instead of what is the difference between this question and the previous question? Instead of 1, we have a here, and the power of x is not 1, it is p. So let me write the first step. In the first step, we write the limit and we assign a variable for the upper bound of integration, let's say t. T tends to infinity, and we have a for the lower bound of integration, and we can write 1 over x to the power p as x to the power minus p dx. Now we can apply fundamental theorem of calculus. Let's first write this limit expression. T tends to infinity. What is the limit of this expression? This is x to the power minus p plus 1 divided by minus p plus 1, and x is from a to t. Putting the boundaries of integration instead of t, we have this expression. I substituted this. And look at the power of t here. When we have two cases. The first case, when p is greater than 1, in this case, minus p plus 1 becomes negative, right? So the power of t becomes negative. So you have 1 over t to the power minus p plus 1 in this case, and when t tends to infinity, this term tends to 0. Okay? And the second case, when p is smaller than 1, in this case, minus p plus 1 becomes greater than 0. So what does it mean? When t tends to infinity, this part approaches to infinity. This is why the result will be infinity. Okay? So let's write these expressions properly. In this case, this limit expression is equal to, we have two cases. When p is greater than 1, this expression will be 1 over, since we have a minus here, p minus 1. If p is smaller than 1, in this case, the result will be infinity. It means the given improper integral is divergent, not convergent. What about the case p equals 1? Let's also look at this case. If p is 1, you can easily change the question here. So the new question becomes integral from a to infinity dx over x. This is the case p equals 1. Okay. So you can assign a variable instead of the infinity. Let's say this is t. So you have this limit expression dx over x. And we know that the antiderivative of this is equal to 1 is equal to ln x. T tends to infinity. Let's use the boundaries of integration. We have ln t minus ln a. And we know the graph of ln function when t approaches to infinity. Ln t goes to infinity also. So the result of this integral is infinity. This is why when p is equal to 1, the given improper integral is also divergent. So you can put an equality sign here. So this problem is done. Let's look at the second example. In the second example, the lower boundary of integration is minus infinity. So we can use this rule of improper integral. Let's first assign a variable for the symbol minus infinity. Let's say limit. Instead of minus infinity, let's have t as a variable. So we have 0 here. T tends to minus infinity. Dx over square root of 3 minus x. So we can continue. What is the antiderivative of this function? Using the substitution rule, you can easily find the antiderivative. Limit t tends to minus infinity. The antiderivative is minus 2 square root of 3 minus x. And x is from t to 0. If you use the boundaries of integration, you have limit t tends to minus infinity. Okay. Using the boundaries, we have minus 2 square root 3 plus 2 square root 3 minus t. Okay. So what is this integral? Of course, this is a number. When t tends to minus infinity, you have an infinity here. This is why the result is infinity. What does it mean? If the limit is infinity, the given improper integral is called divergent integral. Okay, this is done. And the next question, let me write this improper integral as the addition of two improper integrals. I mean integral from minus infinity to 0. You can pick any number. I choose the number 0 here and write the integrand. This is 1 over x squared, dx over 1 plus x squared. And the second integral is from 0 to infinity, dx over 1 plus x squared. Now we are ready to find the antiderivative. Let me first find the antiderivative of this function without using the improper case. And as you know, this is arctangent x, right? So, and also please consider the graph of arctangent x. This is the graph of arctangent x. So let's assign a variable for minus infinity and plus infinity as we did in this rule. So this expression is equal to this limit expression. Finally, putting the boundaries of integration, we have this limit. We have these limit expressions, and we know that arctangent 0 is 0. Look at the graph of arctangent x, which is given here. And when t tends to minus infinity, or x approaches to minus infinity, look at the graph. The function, when x tends to minus infinity, the function tends to minus pi over 2. So you have minus pi over 2 here. Okay, look at the second limit. When t tends to infinity, what about arctangent t? When t tends to infinity, when x tends to infinity, the function approaches to the point pi over 2. So you have pi over 2 here also. I am sorry, the sign of this expression will be minus, not plus. This is minus and this is plus. Okay, I made a mistake. So you have pi over 2 plus pi over 2, which is pi. Since the answer of this limit expression, let's go back. Since the answer of these two limit expressions are a number, not infinity, the given improper integral is called convergent. And this improper integral converges to the number pi. Now we have a second type, improper integrals. This type of improper integrals refers to integrands that are undefined at one or more points of the domain of integration. Let's say from A to B. Okay. We can get an intuitive sense of this concept by analyzing the improper integral from A to B, f of x dx. Okay. Graphically, here we assume that this function is continuous on the interval, open interval A and close interval B. And so this function is not continuous at the point A. Okay, this is our assumption. Look at the first graph. As you see, the yellow one is the function and it is not defined at the point A. This is the vertical asymptote. And you have the point B here. It is defined at the point B. So what do we do in this case? We let t, a variable, be a fixed number. Let's say t be a fixed number here. Okay, we assign a variable. Let's say this is t. So we let t be a fixed number in the interval AB. Okay, in this closed in the semi-open interval. Then by taking the limit as t approaches to the point A, we take the limit as t approaches to the point A from right, of course, we get the improper integral. Okay, so we have three cases here. If the function f is continuous on the interval, close interval A, open interval B, and if f is not continuous at the endpoint B, so in this case, we assign a variable, let's say t, okay, and we approach to the number b, which the function is not continuous there. So we can write this improper integral as a limit form. Look at the second case. Now f is not continuous at the point A instead of b. It's not continuous at the point A. So this is the interval of integration A and B. The function is not continuous here. You assign a variable. You say this is t. And you take the limit of function, limit of integral. And t approaches to the point A, of course, from right. Look at the first case again. This is the interval from A to B. And the function is not continuous at the point B. So you assign a variable, let's say t, and you write the limit form. You say when t approaches to the point B from left, of course, in this case, you take the limit of a definite integral and then you get the improper integral. Okay, for the first and second cases. Look at the third case. If the function is not continuous at the point which is inside of the interval AB, in this case you separate the given improper integral into two improper integrals. Okay, integral from A to that C, the function is not continuous there, and from C to B. Okay, what about the other case? If the function is not continuous at the endpoints, at x equals A and x equals B, in this case you also choose a number C. This is all up to you. You may choose 0, 1, or whatever you wish, and you break the improper integrals into two improper integrals, and then you add them up, you finally get this result. If these limits are convergent, in other words, if the answer of these limits is a number, in this case you say that the given improper integral is also convergent. If one of them is divergent, look at the third case, if one of them is divergent, then the given improper integral is also divergent. If the answer of this limit is infinity or minus infinity, in this case the given improper integral is called divergent. Okay? So let's try to understand this concept by some examples. Look at the first example. Determine if the following integral is convergent or divergent. And the rule is given on the right hand side of this page here. Look at the function, look at the integrand. This is 1 over square root of 3 minus x, and look at the endpoints. Is the function, is the integrand continuous at the point 0? Yes, this is continuous. What about the upper bound of integration? 3. The function is not continuous there. Okay? This is why this function is improper. This integral is improper integral. Okay. So what do? We have a rule here. We should apply this rule. We must assign a variable for the problem point. Let's say the variable is t. Okay, I gave the idea before. So we have the integral from 0 to t, and t approaches to the point 3 from left. Okay, we write the integrand. This is dx over square root of 3 minus x. I actually solved this problem before. This is the antiderivative of the integrand. Now it's time to plug the boundaries of integration. So we have limit when t approaches to the point 3 from left, minus 2 square root 3 minus t. Then instead of x we have 0, 2 square root of 3. Okay. The answer of this limit is equal to 2 square root of 3. What does it mean? Since the answer of this limit is equal to a number, this improper integral is convergent. Convergent improper integral. What does it mean? The answer of this improper integral is equal to that number. Let's look at another example. We have ln x function. What's the problem point here? When x is equal to 0, ln x is not defined. As you know, ln function is defined only for positive numbers. This is why 0 is a problem point. And we have this case here. Okay. In this case, you assign a variable t, and t tends to that number from, of course, from right. Okay. So what does it mean? Instead of 0, I should write t here. Integral from t to 1 ln x dx. In this case, you can directly apply fundamental theorem of calculus. What is the antiderivative of ln x function? This is x ln x minus x ln x minus x, and x is from t to 1. Don't forget to write the limit expression here. T tends to 0 from right. What is the next step? The next step is just plug the values of integration here. Then we have limit t tends to 0 from right. For the point 1, we have 1 times ln 1, which is 0, and minus 1. Okay, for the point t, we have minus t ln t minus minus plus for this term plus t. Okay, so what is the limit of this expression? We have minus 1 here. It is not dependent on the limit. Minus this minus limit of ln t divided by 1 over t. t tends to 0 from right. When t tends to 0 from right, ln function tends to infinity, minus infinity, and denominator tends to infinity. We have infinity over infinity case. This is why we can apply L'Hopital's rule. The answer of this equal to minus 1 minus applying L'Hopital's rule. We have limit t tends to 0 from right. 1 over t divided by minus 1 over t square. This is equal to minus 1 minus, if you substitute, you have t tends to 0 from right minus t, and finally the answer is minus 1. So what does it mean? Since the answer of this limit expression is minus 1, the given improper integral is convergent and it converges to the point minus 1. This is all. What about the next question? Determine if the following integral is convergent or divergent. What is the problem point for this function? The function is defined at the point 0. Okay. Does it define at the point 4? Yes, it is defined at the point 4, but the function x over x squared minus 9 is not continuous at the point 3. And this case is given here. So what do we do in this case? We separate this improper integral into two improper integrals. Integral from 0 to 3, since the function is not continuous at the point 3. X dx over x squared minus 9. This is the first part. And the second part, integral from 3 to 4. X dx over x squared minus 9. In the second step, we use the limit version of these two improper integrals. So this is equal to limit. We have addition of the first and second type of improper integrals. So t, we first assign a variable for the point t, for the point 3. Let's say this is t. Integral from 0 to t. Okay, and t approach to the point 3 from left, since it is an upper bound of integration. X dx over x squared minus 9 plus second improper integral. We assign the variable t for the number 3. So t is here, and t approach to the number 3 from right. Okay, and we have the integrand x dx over x squared minus 9. So what is the antiderivative of x dx over x squared minus 9? Let me write down here. X dx x squared minus 9 is equal to, this is a very easy integral. The answer is 1 over 2 ln x squared minus 9 plus c. Okay. Let's just use this answer and take the limits of these expressions. T tends to 3 from left. Then we found the antiderivative. So the result will be 1 over 2 ln x squared minus 9. Now it's time to write the boundaries of integration. X is from 0 to t. This is the first one. And the second limit when t approach to the point 3 from right. Let me write down the same antiderivative. This is 1 over 2 ln x squared minus 9. And write down the boundaries of integration. X is from t to 4. X is from t to 4. Let's substitute this expression. We get this step. So in this step, when t tends to the point 3 from left, this part tends to minus infinity. What about this expression? When t tends to the point 3 from right, this expression goes to plus infinity. Please remember the graph of ln function. Since the result of one of the result of this limit is infinity or minus infinity, the given integral is called divergent. Okay, it is enough to have one infinity. Okay, it is enough to have one result as infinity to call the given improper integral as divergent improper integral. So this improper integral is a divergent improper integral.